Hello, my name is Pius and I'd like to welcome you to this video on the Babylonian square root algorithm. It's about 4,000 years old and still in use today on most calculators and computers. It's extremely simple to use and its proof is surprisingly simple and short. And it's got a couple of bonus features which will be covered at the very end of the presentations. And briefly, one, it can be considered the first infinite step algorithm producing infinite objects, and provides a great pathway insight into the true nature of general number representation. Now, one thing you can ask is, why was a square root algorithm important to the Babylonians, and why is one important today? A good way to answer this is to look at positive integers only. That's 1, 2, 3, 4, 5, 6, 7, etc. And that's all that's needed for illustration and for the proof. And when you look at other numbers besides positive integers, there will be just a minor alteration for numbers between 0 and 1. Everything will apply. Firstly, multiplying an integer by itself is called squaring the integer. For example, squaring 3, as 3 times 3 equals 9. And you can produce a list of such squares. Yes, consider the first 10 integers. If we square each integer, we'll produce the list on the second line appearing here. For instance, 8 squared is 64, 9 squared is 81. You may remember this from your times table. So integers on the second line are the squares of the integers on the first line. Looking at numbers on the second line, you can ask which number was the root of the squaring that gave rise to that number. So the integers on the first line are called the square roots of the integers on the second line. Now, this is only a list of square roots of some integers ranging from 1 to 100 when we're looking at the second line. Now we can ask, from the list we have, what is the square root of 2, 3, 5, 6, and so on? Looking at this second line, there are some numbers that are omitted. Their square roots are not there. So that's why we wouldn't be able to call it a table exactly. It's only a list of some integers between 1 and 100. It's a list of square roots, not a complete table. Now, a good way to look at the integers is to split them into blocks of 50 and look at their square root features. Starting from integers from 1 to 50, here is a list of selected integers, and you may recognize them from the table we've just had or from your times table. Now, in that block of 50, you can say that these box numbers, their exact square roots can be written down in a list or a subtable, okay, as we've just seen on the last list we looked at. Now the rest of the integers, do you know their square roots? I don't think so, and there's a very good reason why, and we'll discuss that shortly. But the unboxed integers, their square roots will have to have an infinite number of digits after the decimal point. And further, the infinite number of digits will not form a pattern. So their values cannot be captured in a list. And looking at that block of 50 without the ones that were on a list, to see that most of the integers between 1 to 50, their square roots cannot be captured in a list. So what happens is that their values will have to be approximated. Now, a couple of examples to make the meaning of approximated clear when we're looking at these square roots calculations that we can make. Firstly, consider this number. It's a repeating pattern, 2.0004, and the 3 dots signify that goes on forever, but it's a repeating pattern of zeros. But there are just 9 digits written here, so there are 9 zeros after the point, and from these 9 digits, we could write down this number to 2 places, and that would be 2.00, or we could write it down to 5 places, 2.00. Although we've been given just 9 places and we know it's a repeating pattern, we can therefore predict the 10th digit is going to be 0. Okay. So you can summarize this as you can write down to 2 places, 5 places, and predict the 10th digit. Now let's have a look at another example of a repeating pattern, but this time not zeros, and this one is 3.125, 125, 125. Again, it's a repeating pattern, and they're just 9 digits written here. Again, we can write this down to 2 places, 3.12, to 5 places, 3.125, 12, and we can still predict the 10th digit as a 1. Why? Oh, because it's a repeating pattern of 3 digits. There are 9 digits written down. So the 10th digit, the pattern begins again. So it has to begin at 1. And in fact, we can predict any further digits after the 10th digit, any digit we like, by using the fact it's a repeating pattern and working out which digit it will have to be. So we can summarize this saying that from the 9 written digits, we can write down to 2 places or 5 places and predict the 10th digit, even though we were only given 9 digits, because it's a repeating pattern. Now, an example of a non-repeating pattern, and this one is the value of square root of 2. Now, this is a pattern that doesn't repeat. And that's because it's a special type of number called an irrational number, which has the property that its digits cannot repeat, and that's quite straightforward to prove, and that will be covered in another video, or you can look at Wikipedia for proof of that. Now, they're just 9 digits written here, and again, from the 9 digits, we can write down the number to 2 places, 1.41, to 5 places, 1.41421. But can we predict the 10th digit? And the answer is no, because the pattern doesn't repeat. We have no idea what will be the digit, and we would have to calculate it. So we can summarize this and say that, again, we can write down to 2 places, 5 places, but can't predict the 10th digit place. So this is the meaning of approximated. We can write down or work out some initial digit places, but further digit places are unknown, unpredictable. And if desired, these further digits will have to be worked out. Now going back to our list of integers from 1 to 50, we have these integers which we've seen can be put in a list, and the rest of the integers, the unboxed numbers, can only be approximated when we're looking to find their square roots, in the sense, approximated in the sense we've just discussed. Now, if we remove those integers that can be put in a list to those that can be approximated, we see that those whose square roots can only be approximated are the vast majority in the integer list from 1 to 50. Going on to the next block, from 51 to 100, you may recognize these numbers from your times table. Their square roots, for 64 it's 8, for 81 it's 9, and for 100 it's 10. Now, the rest of the remaining integers are these, and their square roots can only be approximated. And note, there are only 3 box numbers in this second block, which is down from the last block. And if we remove those box numbers, we find once again that the approximated square roots in this second block form the vast majority. And in fact, as you go consider further blocks, you will pretty soon come to some blocks where all the integers, their square roots can only be approximated, and none of them can be put in a list. And it's one thing to note, it's easy to prove if an integer is not an integer square, its square root can only be approximated. That kind of proof is covered in when you look at irrational numbers, which is covered in another video presentation. Now, looking at the integers from 2541 to 2550, and from 251 to 260, we'll find that these are 2 blocks next to each other, and both blocks, every single integer has an approximated square roots. So what that shows is that you'll start getting blocks of 50 next to each other, in which, again, all the square roots will have to be approximated. And these blocks will continue to get longer in length, pretty soon you can have 10 blocks or 1,000,000 blocks, and it goes, and there's no end to the length of the blocks that will be formed. All of this was just to show that it seems pretty clear that when you look at square roots of integers in the general form, most of them, just about all of them, have to be approximated when you're looking at square roots. So the takeaway is that finding square roots of integer numbers needs an approximation method. And although square roots of integer squares can be exactly found and written down, the percentage of these square roots of integer squares to square roots of other integers is negligible. So square root approximation methods were essential and the only option really then to the Babylonians and today. Quick note, those square roots of integer numbers that didn't have repeating patterns of digits were examples of irrational numbers, and as we've seen, practically all square roots of integers don't have repeating patterns of digits and so are irrational. Now, irrational numbers is a really fascinating topic and coverage is planned for the future. Now let's have a look at the actual method. Let's say you need to find the square root of positive integer n. Step 0. Let x0 be any integer at all. Step 1. Let x1 equal the number that you want to find the square root of, which is n. You divide that by x0 and then add x0, and once you've done that, you multiply everything by a half. And looking at that formula on that line, we can reference the value of x0. Notice the value that we got in the last step. Step 2. Let x2 equal n, which is the number you're trying to find the square root of, divided by x1, and then add x1, and when you've done all that, multiply everything by a half, and the reference for the value of x1 is the value that was got in the last step. Step 3. Exactly the same thing again, except you replace x1 by x2. So x3 is n divided by x2 plus x2, and everything multiplied by a half, and x2 is the value you got in the last step. Step 4, I think you're beginning to see the pattern now. It's exactly the same as step 3, except you're using x3 as a substitute for x2 and computing a new value. And of course, x3 is the value that you got in the last step. And you continue until you've got the desired number of digits accuracy. Let's have an example. Let's say you want to find the square root of integer 7 to 4 places of accuracy. First step, choose any number or any integer, and we'll choose 2. I must stress, any number could have been chosen. 2 is chosen. Step 1, let x1 equal 7, which is the square root, which is the number we want to find the square root of, divided by x0, and then add x0 to that, and then multiply everything by a half. And of course, looking at that line, x0 is referenced as the value we got in the last step. When we make that substitution of x0 equal to 2 into that expression, we'll have 7 divided by 2 plus 2 and everything multiplied by half. We calculate that and we have 2.75 as the answer. Now we've got x1. Step 2, let x2 equal 7, which is the number we want to find the square root of, divided by x1 plus x1 and everything multiplied by a half. And x1 is the value that was got from the previous step. We make that substitution, we get 7 divided by 2.75 plus 2.75, everything multiplied by a half. Make that calculation, and we have this number. Step 3, now we have the x2. Step 3, we do exactly the same thing again, and we make x2 is the value that we got in the last step, and we make that substitution, do the calculation, and the answer we get is this. We can stop now and pause and look to see how many places after the decimal digit are agreeing. At this moment, we've only got 0.64, which is the same in x2 and x3. We've got 2 places that are agreeing, not 4 places, so we continue. x4, again, the same form as before, and x3 is the value that we got in the previous step. We make that substitution into the calculation, and we have this number. And we pause again, and to see how many places are agreeing after the decimal point. At this point, we've got 5 places that are agreeing. That's 0.64575, the same in both x3 and x4. We're only looking for 4 places, so we can stop now. And you may wonder why we can be sure that these places, these decimal digits won't change the further we do the calculations. Once you look at the proof, it will be easy to see that these numbers will remain stable. Okay, so we can stop. We've got 4 places, and we can round that up to 4 places, because 5 is the 5th decimal digit there. So the answer is 2.6458. Quick check on the calculation, and we have the answer as 7.0025764. And now you may wonder, will we ever get to a stage where we can have complete zeros over there after the decimal point? And the answer has to be no, because as we mentioned, the square root of 2 is one of those integers whose square root has an infinite number of places, and if we write down only a finite number of places, we can never have an exact answer where we have complete zeros on after the decimal point in the answer. Okay. Now, quick review of what we just did in that last step is that we needed to find the square root of a positive integer n. We carried out these steps, and in each stage, the value that was used in the calculation in each line, its value was got from the previous step. And we continued until we had the desired number of digits accuracy. Now, we can summarize these repeated steps in a formula scheme. This is xn plus 1 equals n, the number we're trying to find the square root of, divided by xn, and add xn to it, and multiply everything by half. And xn is the value that was got from the previous step. So looking at this line, n can be will take on any value from 0, 1, 2, 3, 4, 6, and so on. And x0 was any integer that was chosen to start off as an initial value. And you can look at this formula scheme as it's a way of generating new numbers, and it's the new number equals n, the number you're trying to find square root of, divided by the old number that you previously have, and add the old number again and multiply everything by half. It's just a way of generating new numbers. That's one way to look at this formula scheme there. And x and the number of steps chosen depends on how many digits, places of accuracy are required. And x0 is any integer. And this is an example of an iteration formula. Now, one thing to ask is, how does the square root algorithm work? Well, a surprisingly easy proof is given in the part 2, the second video. And for those of you curious as to know why this always works and guaranteed to give you a square root to any desired places of accuracy, I invite you to join me in the second video. Thank you.